So we're going to get started by thinking again about this linear transformation picture that we keep returning to, right? The picture of what it looks like to take a domain, which is a vector space, and then relate the elements of that domain to elements of a codomain using a linear transformation. And so if I have a vector v, I can drag it around to various places in the domain, and I can look at where is its image in the codomain. But for a square matrix is a standard matrix of a linear transformation from a domain to a codomain that have the same dimension as one another, right? So it's, for example, in this cat example, it's a two-dimensional domain being related to a two-dimensional codomain. So we don't have to see the domain and the codomain as separate. We can actually lay them on top of one another to make things a little bit easier to understand, right? And that's what we start to do here. And what I see when I sort of move around my vector v, I can also look at what's happening with this image vector av, and I can look at those both on the same coordinate system, right? And so what we're going to end up trying to look for is we want to look for examples of vectors that this linear transformation is changing their not changing their direction, but is only changing their magnitude. So can I find an example, speaking geometrically, can I find an example of a vector for which its image is parallel to the original vector itself? Right? So this doesn't seem to satisfy that. This doesn't seem to satisfy that. I have an acute angle here. I have an obtuse angle here between the vector and its image. This doesn't work because it would be anti-parallel, but it looks like this does, right? So here's an example of a vector that looks like the image of that vector is parallel to the vector itself. So can I find an example of such a thing? And then similarly, can I find an example of a vector whose image is anti-parallel to itself? Right? So we can start with those couple of questions, because if I find those things, then what I'm finding are sort of directions in the xy plane in this example that my linear transformation is acting not like a matrix, but it's acting like a scalar. And that's what we want to eventually start to hunt for, because that's going to tell me what how lengths are being changed by linear transformation. Instead of just looking at volume, which is sort of an aggregate change of size, we want to look at changes of length, which are kind of individual elements of a change in volume. So the first matrix we worked with was 1, 2, 2, 1. And the question is, can we find vectors for which v is parallel to its image? And can I find vectors that are anti-parallel to their image? And the answer for this matrix for both questions was yes. For example, 1, 1. Was a vector that is parallel to its own image, and 1 minus 1 is an example of a vector that was anti-parallel to its image. Right? The image of v is av here, which is along the same line and in the same direction as v itself, and the image of w is aw, which happened to be exactly opposite in the exactly opposite direction as w was. And so we can find both a parallel example and an anti-parallel example for this particular matrix. And so what becomes interesting is how do we operationalize that as an algebra question, right? It's pretty clear as a geometric question, and we can do it if we have this tool. We can drag the vectors around and see where they go, right? But it's when we want to turn that into an algebra question that things start to get a little bit more interesting. And so the way that this group operationalized those questions is that we're looking for vectors x for which... I'm going to share my screen because it's probably blurry as usual. We want to find vectors x such that ax, in other words, the action of the linear transformation on the vector, is the same thing as c times x for a scalar multiple c. Right? So such a vector is being acted upon by a linear transformation, which in general turns multiple dimensions into multiple dimensions. But for this particular vector, that transformation is just acting like a single scalar multiplication. Right? Ax is equal to c times x. And in the case of parallel, we want c to be a positive real number. In the case of anti-parallel, we would want c to be some negative real number. Right? And so what this begins to do for us is it begins to build up kind of a dictionary of when, let's sort of write it like this, when ax is equal to c times x, and in the case when c is positive, we end up getting a transformation which stretches in a parallel fashion. right? X is being stretched, its direction, its length is being changed, but its direction is not being changed because its image is parallel to the original. And then likewise, if C is a negative real number, not only do we stretch it, but we also reflect it. Reflect over the origin, right? Because that's what happens when you multiply a vector by a negative scalar, right? It flips its direction to exactly the opposite of the direction that it used to have. And then it might also get stretched or shrunk in its length. Its magnitude might change, but its direction is exactly opposite of what its original direction was. So the rest of the analysis that we do today is going to be about this equation, right? Ax is equal to some constant times x, some scalar times x. We want to figure out when does a matrix, a linear transformation, behave like a single scalar does, right? And clearly that doesn't happen for just any vector, right? For most vectors, I would say, AV and AW are not either neither perpendicular, parallel nor anti-parallel to the original vectors that we started with. But for some magic vectors, and an interesting question is how many, right? For some magic vectors, V is parallel to AV, or W is anti-parallel to AW. And so we want to figure out how to find those. But as we've figured out pretty quickly in this exercise, it also depends on the matrix. And so when we looked at some other examples, like 2 minus 1, 0, 2, how is this example primarily different? What kinds of things happened here that didn't happen in the first case? So for this matrix, we can find a parallel stretch direction, right? A positive real number C that is multiplying my vector and sort of changing it into a parallel multiple of itself. But we couldn't find any way to get anti-parallel. It looks like there's always an acute angle in between any vector and its image for this particular transformation. And so what is it about the action of this transformation on my cat face that is also kind of telling me that story? How do I know that we're not getting any anti-parallel directions based on what the picture of this cat face looks like in the image? So in our first example, if I dial back to that one for a brief second, 1, 2, 2, 1, the image of the cat in the codomain is reflected relative to its original. And the reason that it would be reflected is that we had an anti-parallel direction. We had a flipping direction, right? It's almost like this direction is telling me what is the axis along which I'm reflecting, right? I'm reflecting along an axis perpendicular to this line y equals minus x, if you like. And along the line y equals x, I'm just stretching in a parallel fashion. So I'm stretching by some factor along the line y equals x, but then I'm also reflecting across the line y equals x according to this anti-parallel flip direction. But we lost that anti-parallel flip direction when we looked at the second example. And so we also lost the fact that we had a reflection there in the first place. So we have an orientation preserving transformation this time. We have no anti-parallel flipping. There's something else that's important about this one that I'll fill you in on. And that is that, in fact, there's no other direction besides this one direction in which there is ever a case where A times a vector is a scalar multiple of that vector, right? So there were two directions that had that scalar multiple property before, but there's only one direction in this case that has that scalar multiplication property, which is kind of interesting. So then in the third example, 2 minus 1 minus 4, 2. Dial that back here. 2 minus 1 minus 4, 2. Something very interesting has happened here. What did you say was the difference with this example? Well, first of all, where's my cat? The cat is flat. What does that mean?
It's squished onto one dimension.
0?
Yeah, it's squished onto a one-dimensional image, right?
Oh.
This matrix, 2, negative 1, negative 4, 2, if you find its image, a basis for its image is just the vector negative 1, 2, right? Negative 1, 2 being this vector right there in my codomain, right? That vector is a basis for the image. So the entire two-dimensional plane is being squished onto this line y equals negative 2x. And so that includes my cat face, right? The cat is still there. It's just all squished down onto this one-dimensional image. Can I find a direction of parallel stretch? Can I find a direction of anti-parallel stretch? What's the best that I can do here?
Only parallel?
I can find only a direction of parallel stretch. I could find it right about here or so, right? So there's a direction of parallel stretch. But then there's also a direction of another magic kind of stretch, namely the stretch by a factor of 0. Remember, if I have a linear transformation from 2-space to 2-space, whose image is only one-dimensional, what else do I know about that transformation? If we've gone from 2-dimensional down to a one-dimensional image, what else must also be one-dimensional?
The kernel?
The kernel. The kernel of this linear transformation has to be one-dimensional by the rank nullity theorem, right? If we go from 2 dimensions to a one-dimensional image, that extra dimension has to be accounted for by the kernel, the space of vectors that is getting sent to the 0 vector by this linear transformation. So if we look closely at this W that I just drew here, this W is getting sent to the 0 vector in the image. I'm going to have to tweak it just a little bit more to get it to the 0 vector. There it is. So secretly, there is a direction of a 0 squishing, if you like, right? Where the image is a 0 multiple of the original vector. So we have parallel stretching, we have anti-parallel stretching, and then we also have 0 stretching, which is otherwise known as projection, right? So there's a direction, the kernel direction here, along which we're sort of squishing everything in this 2-dimensional plane away, including this cat face. So that's something that's different here. And then in the final example, 1 minus 1, 1, 1, if I switch to that, what ends up happening here? Where are my parallel directions? Where are my anti-parallel directions? What's happening that's different?
You get neither because the cat's just rotated?
We get neither because all that's happening here, apparently, is a rotation, right? Well, I won't say all that's happening. There's one other thing that's also happening at the same time as the rotation.
And a scale.
Right. It looks like we're blowing up the cat to be a bigger cat, right? So it's getting bigger and it's rotating by some angle. In particular, it looks like it's probably a 45-degree angle in this case, right? Because this vector 1, 1 appears to make the 45-degree angle with 1, 0, which was its pre-image. So, right, so because this is just a rotation, we're not going to find any direction where there's a parallel stretch or an anti-parallel stretch for my vector. And so it's worth thinking about, what is that going to mean about this equation ax is equal to a constant times x? Right? If I try to solve that equation in this matrix, right, what's going to happen? Right? Is there just going to be no solution? Well, that doesn't seem to be plausible because certainly the 0 vector is always a solution of this equation. So I'm going to sort of modify this to say that we're only really going to be interested in non-zero vector solutions to this. Because it's pretty, I think it's pretty immediate to see if I put x equal to the 0 vector, then the left-hand side of this equation is going to be 0. The right-hand side of this equation is going to be the 0 vector. And so, of course, the equation will be satisfied when x is equal to the 0 vector. And so it's non-zero solutions of this equation that we're really ultimately most interested in. And so we want to understand how the solutions, not just the vectors that tell me about the directionality of the solutions, but also, maybe more importantly, the scalars, the C's. What do those tell us about the individual geometries that are included in these linear transformations?